Hey guys, this is Mr. Bennett, and this is video 7-4. We've got two big ideas in this video. The first idea is we're going to talk about naming ionic compounds, something that we've already practiced in class. So this is going to be kind of a review, just something you can look back at and double check yourself on. And then second of all, we have metallic bonding. This is a brand new idea, brand new concept. We've talked a lot about ionic bonds. Now we're going to move on to a different type of bond. So, as I said, ionic compounds naming we've already discussed, so I'm going to try and cruise through this as fast as possible, but still give you enough information to look back at if you still need help on this. Ionic compounds are always made up of two things. They're always made up of a cation and an anion. Cations are positive, and then anions are negative. So you always have that positive component and the negative component. Now, your positive can either be a metal or a polyatomic ion, something like ammonium. Anions, on the other hand, will always be a non-metal or a polyatomic. Polyatomic ions would be things like, anions would be things like hydroxide or phosphate. So when we name these, you're going to have to name the two components, the cation and the anion. You always name the cation first, just like the formula rule. So when we write the formulas for a cation or for an ionic compound, such as this one, the cation, rubidium, is first. Okay, so when we name it, same order. The cation comes first, and we simply name it after the element or the polyatomic that is serving as the cation. So in this case it was rubidium, so we call it rubidium. In this case it's ammonium, so we call it ammonium. NH4 is ammonium. So naming the cation portion is really easy. You just find out what it is and you write the name. The anion gets a little trickier. If it's a non-metal, then you have to change the name slightly. So for instance here it's chlorine. So we have to take the first section of that name, which is chlor, and then we give it an "ide" ending, so it becomes chloride. If it's a polyatomic, it's easy. You simply figure out what polyatomic it is, and you write the name. So this is rubidium hydroxide. This was rubidium chloride. All right. Now, if the ionic compound contains a transition metal, there's an extra step. Okay. You still follow the same rules. So the metal is going to be listed first because it's the cation, and the non-metal or polyatomic is still going to be listed second because it's the negative ion. How do you know if you're going to need to do this? Well, your metal is either in the D block or it's under the stairs. Okay, which means it's a transition metal. So that's the sign that you're going to need to do this. Once you figure out that yes, you're dealing with a transition metal, then you have to figure out its charge. That's your first step, because the charge is going to be part of its name. So here I have manganese. Manganese is in the D block, so I know that it's a transition metal. So the first thing I do is I figure out what the charge of manganese is. To do that, we need to do the whole working backwards method. So I have my formula. Okay, I need to work backwards. I need to figure out the charge that I know, and then use that charge to figure out the charge, the other part of the ionic compound, that charge that I don't know. So we always know the charge of the nonmetals. The nonmetals, they don't change. Okay, so for instance, oxygen, when we look at it on the periodic table, has a charge of -2, always. And we know that in this compound we have two oxygens. If they each have a charge of -2, that'd be -2 times 2 oxygen ions. That would give us a total charge on this side of -4. We know that this whole compound, the charge of the entire compound put together, needs to add up to be 0. So the positive side needs to be equal yet opposite to the negative side. So it'll be positive and the same charge number. So if this side has a total charge of -4, this side is going to be +4. Now in the formula, we only have one manganese. That means that this whole +4 belongs to the manganese. So when we look at this, we're really looking at a manganese +4 ion combined with 2 oxygen -2 ions, okay, or oxide ions, I guess. That's what we're really looking at when we look at this formula unit. So how do we name that? Okay, once we figure out the charge, this is what we really were looking for, then all we do is we write out the name of the metal. So in this case, it would be manganese. We look at the charge number, which is 4, and we write that in Roman numerals. So there we go, IV, 4. And then we follow up with the same method for the nonmetal as we did before. So this is oxygen, so we use the ox, and then we give it that "ide" ending. Okay, that's a transition metal. So what I'd like you to do now is practice naming ionic compounds. So pause the video, name these, and then start it up and see if you got it right. Okay, hopefully you're pausing it. It's important to try and then come back and see. All right, let's see how you're doing. So it says name the following ionic compounds. Let's see what we got here. We've got potassium and bromide. So this is going to be potassium. I know that because that's the cation, right? Potassium, and then the anion, I'm going to take the first part of it, which is brom, and then give it an "-ide" ending. Here we have magnesium. That's our cation. It's our metal. And then it's combined with the non-metal iodine, which we're going to change to iodide. Okay. Here we have a polyatomic serving as our cation. NH4 is ammonium. Okay, and then it's combined with the anion or non-metal sulfur. So we take the sulf and then we give it that "-ide" ending. Last but not least, here our metal is lithium. And we're going to combine it with the polyatomic phosphate. So hopefully you got those. If not, probably because of your polyatomics. So go back and check those. If not, ask me tomorrow and we'll see what we can do to help you out. Alright, second topic, second big topic. As I mentioned earlier, metallic bonds. Up until now, we've dealt with ionic bonds. Ionic bonds always form between a cation and an anion, meaning you always have a metal and a non-metal, or you have a polyatomic and a non-metal, or you have a metal and a polyatomic. Those are the three ways that you can get these. Now these bonds form because you're transferring valence electrons, meaning you're moving an electron from the cation to the anion, and that's what's going to create. As this loses that electron, it's going to be it's going to have a positive charge, and the anion gaining the electron is going to have a negative charge. And an ionic bond is really that positive being attracted to the negative, and they stick together. That sticking together like magnets, that's the ionic bond. Metallic bonds, our new type of bond, only occurs between metals. So this bond forms as a result of metals interacting. And the way they're interacting is they're going to share valence electrons. They're not transferring, that's ionic. They're sharing them, but they're sharing those valence as a sea of electrons. So this is really the key phrase here. When we're talking about metallic bonds, it's all about the sea of electrons. That's going to give us all the properties of metallic bonds. Things like weak bonding strength, high melting, high boiling, solids at room temp with the exception of mercury, and they have the ability to conduct electricity and heat. Now one thing I do want to point out, just because they have weak bond strength, I know we think of metals as being really strong. It's not that they have weak bonds and that means it's a weak substance. It means that the bonds are adjustable. Because they're weak, they have the ability to slide a little bit, rearrange, and adjust, and we'll see that that's one of the reasons why metals can do what they do. So what does the sea of electrons mean? As I said, this is the key phrase when you're dealing with metallic bonds. If you ever see sea of electrons, that first thing that should come into your brain, to your mind, is that these are metallic bonds that we're talking about. The sea of electrons means that your valence electrons are shared, but they're shared so much that they do not belong to any one atom. If we look at our picture down here, we have all these positive nuclei, and these black dots represent the electrons. They're just moving around every which way. Okay, they're the valence electrons, and they're not hanging out with any one particular atom. They're simply moving around from atom to atom to atom to atom, constantly flowing. They're free floating around the positively charged nuclei. So there's no permanent bonds between the atoms. They actually have the ability to kind of slide past each other a little bit. And because the electrons are flowing, they're going to allow things like electricity and heat to move around. They're going to carry it. They're going to conduct it. This also means that it's ductile or malleable, meaning you can form it into a wire, you can pound it flat, because those weak bonds allow these atoms to be kind of slide past each other, I guess, the way to say it. They can slide past each other. You can adjust those bonds. You can pound it flat. You can change the shape a little bit. It doesn't mean it's going to be easy. Some metals are really hard and changing the shape is really difficult. But as a whole, metals have this ability because of that sea of electrons. And last but not least, they form really strong solids because you have this really strong electrostatic attraction, meaning positive attracted to all these negative electrons that are floating around in a sea. Okay. Now the last idea I want to mention with regards to metallic bonds is that because of metallic bonds, we can form very, very special mixtures that we call alloys. Anytime we combine different metals, we create an alloy. An alloy is really just a mixture, and it's a homogeneous mixture. So it's always going to be different metals being combined, with the exception of occasionally you can do it with non-metals as well. Okay, so to rephrase, alloys are combinations of different metals, sometimes non-metals as well, in a homogeneous mixture. But the big thing is you're using metallic bonds. Okay, so you're using metallic bonds. Let's look at some properties. Well, let's look at some examples here. But the key thing that we're going to see as we look at these examples is that the properties of the alloy are different from the individual components, from the original metals. In fact, they're often enhanced. You make alloys because you want to enhance one of the characteristics or several of the characteristics of the metal. So, if you go back in human history, you may be familiar with may have heard of a time period called the Bronze Age. The special thing about the Bronze Age was that prior to the Bronze Age, tools and things, weapons, were made out of copper. Copper it's a metal, it's strong, but it's also kind of weak, and it breaks and bends. It's not very durable. Well, they discovered that if you add tin to copper, you create an alloy called bronze. Bronze is harder than copper, so you get stronger tools and stronger weapons. So it was a huge technological advancement for the time, because you got stronger tools and stronger weapons by making this alloy. Now, another alloy using copper is known as brass. Brass uses zinc instead of tin, and you get a gold-like appearance, and it turns out brass has a really low friction, meaning it's kind of a slippery metal. So if you need metals to be able to slide past each other, you might want to use a brass alloy. Also, when brass collides with brass, it does not spark. So if you need to use metal around a flammable substance and you're worried about sparks triggering an explosion, then using brass might be the way to go, because you won't create a spark. Now, an alloy that is used a lot in construction is steel. Steel the base metal is iron, and we use a non-metal, carbon, just a small amount, mixed into that iron. And what it does is it gives it a stronger, more durable property, but because we're adding non-metals, remember non-metals are not ductile or malleable, we lose some of the ductility and malleability that iron has. Okay, so we trade some flexibility, ductility, malleability for stronger, more durable metal. Okay, last but not least, especially if you're an athlete, you may be familiar with these. Titanium alloys are used in a lot of sports equipment because by adding titanium to your substance, to your metal, you reduce the weight, but you get higher strength. So baseball bats, golf clubs, lots of different things are made using titanium alloys because you get higher strength, but you also get reduced weight, so it's lighter yet stronger. Alright, and just to kind of show you what I'm talking about in terms of alloys, here would be the pure metal. This would be something like our iron. Okay, then if you mix in another metal, okay, you get this nice almost homogeneous mixture here, giving it those extra properties. And then here we've got our non-metal added in, even giving some more slightly different properties. Alright, make sure that you complete your whisk online, and we'll see you tomorrow.